All right, you guys, this is Note-Taking Guide 5.3 for Mathematical Decision Making for Life. Today we're going to talk about something called a tree diagram, and that's going to lead us to a rule called the fundamental counting principle, which is actually a really easy rule to use. So first of all, a tree diagram is kind of just a physical representation of what's happening with things. So here's our first example. It says a new restaurant has opened and they offer lunch combos for $5. With the combo meal, you can get one sandwich, one side, and one drink. Here's the choices. Sandwiches, you can have chicken salad, turkey, or grilled cheese. Sides, you can have chips, french fries, or a fruit cup. And drinks, you can have soda or water. So it says draw a tree diagram to find the total number of possible outcomes. So we're going to start with our sandwiches at the top of our tree. So I'm going to go chicken salad, and I'm just going to call them by initials. I don't want to write out all the words. I'm going to put turkey, and I'm going to write grilled cheese. Then I'm going to just make it like a tree. So I'm going to go to my next choice, which is chips. So if I order a chicken salad, I could also order chips. I could order french fries, or I could order a fruit cup. Does everybody agree with me on that? What do you think about if you ordered turkey? Would you still have 3 choices for your sides? You would, right? So on turkey, you would still have chips, french fries, or a fruit cup. And even if you ordered grilled cheese, you still would have choices for your side of chips, french fries, or a fruit cup. Is everybody following me on how this tree thing is working? So now we have 2 choices for our drinks, soda or water. So if I do chicken salad and chips, I still get to pick soda or water. If I do chicken salad and french fries, I still get to choose soda or water. If I do chicken salad and fruit cup, I still get to pick soda or water. Do you think there's got to be a better way to do this? Anybody? There is a better way. I'm going to show it to you in a minute. But we're really just drawing a tree that describes our possible outcomes for all of those choices. When we get to the bottom of the tree, it tells us the total possible ways that we had choices for our lunch. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different outcomes for our lunch. Okay? Does anybody know an easier way we could have done that? No? All right, let's look at the numbers up here and see what would have happened. How many choices did I have for sandwiches? 3. How many choices did I have for sides? 3. How many choices did I have for drinks? 2. Can you take a look at those numbers there for me and see if you can somehow magically manipulate them to get 18? Times them all together, says Kobe. What do you guys think? 3 times 3 times 2 is 18. Did that work? That, what Kobe just did, is called the fundamental counting principle. It says if you have a certain number of choices for one thing and a certain number of choices for another thing, you can multiply those choices together and it will give you the total possible number of outcomes that you have for those choices. So sometimes on today's assignment, I make you draw the tree. Sometimes I just ask you for the answer. If I ask you for the answer, wouldn't it make sense that it would be easier just to multiply those numbers together? If I ask you for the tree, then you have to draw the tree. But all right, next example. Brian wants to buy a new bike. He can choose a 10-speed or a 3-speed. The bikes come in red, blue, black, and purple. How many bikes can Brian choose from? Do you already know that? How many can he choose from? So he has 2 choices of kinds of bikes, and he has 4 choices of colors. So how many total choices should he have altogether? He should have 8 altogether, right? We know that from what we just figured out was the fundamental counting principle. But it says to actually make the tree diagram. So I have to go 10 speed at the top and 3 speed at the top. And then I have to go red, blue, black. I should have abbreviated. Purple. I'm going to start abbreviating. Red, blue, black, and purple. That's funny because BL could be blue or black still, right? Whatever. Okay, so did I end up with 8 possible choices? I did. So again, that tree diagram figures out the same thing as that fundamental counting principle figures out for us. The total number of possible outcomes. Okay, questions so far? Are you like, let the whole day be like this? Yeah, it is, the whole day. Third question, the fundamental counting principle says if there are m ways to do one thing and n ways to do another, then there are m times n ways of doing both, which is what I set up there again. If the sandwiches are 3 and the chips are 3 and the drinks are 2, we can multiply those together, which is what that rule says. So here's our last example. I think it's our, no, we have one more on the back. Let's say that you want to flip a coin and roll a die. There are 2 ways that you can flip a coin. You could get heads or tails. And then there are 6 ways that you can roll a die. So that head had 6 different choices to get to. The tails had 6 different choices to get there. So there are a total number of 12 possible outcomes. Again, that was from the 2 here times the 6 here, which gave me the 12 there. That's how that fundamental counting principle works. So instead of having to draw this tree diagram every single time, you can just use that fundamental counting principle and multiply things together. So last example on the back side. You go to the snack bar to buy a bagel and a drink for breakfast. You can choose from a plain bagel, a blueberry bagel, or a raisin bagel. So how many choices on bagels? 3. The choice for drinks include water, sports drink, orange juice, and apple juice. So how many total for drinks? 4. So how many different, it says lunches here, and it should have said breakfast because up above it said breakfast, but how many total breakfasts can be made with these choices? So we had 3 choices here and 4 here. So don't I get to do 3 times 4, which is 12. Nice job, Ashlyn. Okay, questions on how I did that? No?